Good evening, students. How are you all? So welcome to Stuti Academy. I am Kanika ma'am, your mathematics teacher. Now onwards, I'll be taking mathematics session for you all. So first of all, welcome to grade 10. I think it's been almost a month that you've been studying in grade 10. So recently promoted from grade 9. So how are you all feeling? And it's been like a long time you might have gone to school. So now these days we are having offline classes also. So I think most of you in school, you might have started with real numbers. That's your first chapter. Yes. And what was the first chapter in the previous grade, in grade 9? Yes, it was number systems. So this real numbers is also very much related to number systems. So we are going to start with this chapter today. So in primary grades, we started natural numbers, the counting numbers. Like suppose I want to count number of children here, I can count as 1, 2, 3, 4 and so on. I cannot count somebody as 0 or I cannot count somebody as 2.5. So it's the counting numbers 1, 2, 3, 4 and so on. So in grade 6 we started that there is a specific name given to the same, that is natural numbers. They are natural numbers. Now, to this collection of counting numbers, 1, 2, 3, 4 and so on, if I add 0 to it, this becomes a new collection that's called whole numbers. So, all this we've started in grade 6. Now, in grade 7 and 8, we started with a new collection that's rational numbers. So, we've done this earlier also. Rational numbers. Rational numbers are those numbers which can be written in P by Q form, where P and Q, they are integers. Integers means that we can have negative and positive numbers both. And Q is non-zero. So children, why is Q non-zero? Yes, Q is in the denominator. It's in the denominator. Denominator can never be 0. Division by 0 is not possible. Like suppose you have 10 chocolates with you and you have to divide it among 0 students. Not possible. That's not possible. So division by 0 is not defined. So coming back to rational numbers are those numbers which can be written in P by Q form, where P and Q are integers and Q is non-zero. So this we started in grade 7 and in grade 8. Now in grade 9, we came up with a new concept of irrational numbers. So that's very simple. Irrational numbers are those numbers which are not rationals. Like I have irrational numbers, then those numbers which are not rationals, that means which cannot be written in P by Q form. Like for example, we have square root of 2. It's an irrational number. We have pi. The value of pi is also irrational. So this is all we started in grade 9. Now suppose I combine the collection here of rational and irrational numbers, then I get a new collection that is real numbers. So I'm going to combine these two, and when I combine these two, I get a new collection that is real numbers. So together, if we take rational and irrational numbers, we get a new collection that's real numbers. So coming to the definition of real numbers is defined as the set of rational and irrational numbers. Real numbers are the numbers which include both rational and irrational. For example, we have minus 2 by 5, minus 2, 0, 1 and so on. So these are all which can be written in P by Q form. And irrational numbers, we have square root of 3, pi, etc. Like I said earlier, square root of 2 is irrational. I just said square root of 3 is irrational. So square root of all the prime numbers, they are irrational numbers. So all these children, we are going to study in detail in grade 10. Now let's come to the new concept. In grade 9, we have studied postulates also. We have studied theorems also. Now we'll come to a new concept, that is lemma. So lemma is also a statement which is already proved earlier. But this statement, we use it to prove another statement. Like I'm going to take a lemma. This lemma, the statement, lemma is actually a statement. The statement I'm going to use to prove a theorem. Now we have Euclid's division lemma in grade 10. This says, given two positive integers a and b, there exist unique positive integers q and r satisfying A equal to BQ plus R, 0 less than equal to R less than B. Now children, this means, in very simple words I'll tell you, like let's say I have a number 9 and I divide it by 2. So I can write this as 2 into 4, that is 8, and 1 I'll be left with as remainder. So in grade 4, your teacher might have taught you that we have a concept that dividend is equal to divisor into quotient plus remainder. So children, please notice, this is dividend, this is quotient here. So you might have studied this in primary classes also. This is remainder and this is divisor, the number which we divide with. So we can write this 9 as, 9 is the dividend, 9 can be written as 2 into 4 plus 1. So 9 is the dividend that can be written in as divisor into quotient, that is 2 into 4 in this case, plus 1. Now children, please notice here, this remainder will be either 0 or will be strictly less than the divisor. It cannot be equal to the divisor, it has to be strictly less than the divisor. So if we are writing here 0 less than equal to R less than B, that means our remainder is either 0 or it can be 1. It cannot be 2 in this case. In this particular case, it cannot be 2 because it cannot be equal to the divisor. So because if it's 2, we could have written here 5. So given two positive integers A and B, there exist unique positive integers Q and R satisfying A equal to BQ plus R, where 0 less than equal to R less than B. So this is Euclid's division lemma. Now we are going to use Euclid's division lemma to find the HCF of two numbers. So HCF of numbers we've already solved in grade 4 and 5 by prime factorization method. Now we are going to do the same. We're going to find the HCF of numbers using Euclid's division lemma. So for this we have Euclid's division algorithm. Algorithm means that it's a series of well-defined steps which gives a procedure for solving a type of a problem. So if I want to find the HCF of two numbers, I can just write down the steps to find the same. So if I tell you the steps, that this is step 1, this is how you have to go. This is step 1, step 2 and step 3. That means I'm giving you the flow of steps to solve a particular problem. That's called an algorithm. So Euclid's division algorithm we use to obtain the HCF of two positive integers. Let's take two positive integers as C and D, where we have C strictly greater than D. So we have two numbers where C is greater than D, and then we follow the following steps. So we apply Euclid's division lemma to C and D. So we do the same thing. We divide the bigger one. That means we are going to divide the C, the bigger one, by D, that is the divisor. We'll get some quotient. Let's say this is Q, and we'll get the remainder R. So we have C is equal to DQ plus R, where the remainder would be strictly less than the divisor, or we can have remainder as zeros. Now if remainder is equal to 0, then we are going to stop here, and the divisor at this step would be the HCF of C and D. Now this is the case when the remainder is 0. Now what if the remainder is not 0? So I've just discussed this. If remainder equal to 0, D is the HCF of C and D. And if the remainder is not 0, then we'll apply the division lemma to D and R. So the non-zero remainder we are going to take, and we will take the divisor here, and we are going to apply the division lemma to it. And we will keep on continuing the process till we get the remainder 0. Once we get the remainder 0, the divisor at the last step where we get the remainder 0 would be the required HCF. So I'll just explain you how you have to do it with the help of an example. So just see, we have a question here where we have to use Euclid's division algorithm to find the HCF of 135 and 225. So we have two numbers here. As we can see, 225 is greater than 135. So we are going to divide this 225 by 135. So let's see. This is going to go one time and we are going to get 135 here and we will be left with the remainder. So remainder in this case would be 90. So I'm going to put it in the same form. Dividend, that's 225 in this case, equal to divisor, that's 135, into the quotient, that's 1, plus the remainder. So children, please notice the remainder here is non-zero. So we'll have to continue this step. So I'm going to take this remainder and I'm going to take this divisor. I will apply Euclid's division algorithm again to 135 and 90 in this case. So now I'll divide 135 by 90. This is going to go one time. I'll get 90 here and I will have 45 here. So we have 135 is equal to 90 into 1 plus 45. Now please notice children, here also the remainder is non-zero. So we'll have to do this step again. We have to keep doing this till the remainder is 0. So I have this 45 as the remainder and I have this as the divisor. Now 90, we are going to divide by 45. So we can do this orally also. If we divide this as 45, we'll get 2 here. 45 into 2 will give us 90. And finally, please notice we are getting the remainder 0. So we have 45 into 2 plus the remainder, that is 0. Now here the remainder is 0. So we are going to stop here. Now the divisor at this step, as we can see, it's 45. The divisor at this step is the HCF. So HCF of 135 and 225 would be the divisor at the last step where we are getting the remainder 0. So this is 45. I hope children, all of you have understood this. Okay, so even if you've not understood, we'll do one more question of a similar type. Now, these are all the questions which I'm discussing from NCERT exercise 1.1. So, if you have your textbook with you, you can take out exercise 1.1. That's on page number 7. Now, the next question is also based on the same concept. We have to use Euclid's division algorithm and we have to find the HCF of 867 and 255. So, 867, we can see it as bigger than 255. So I'm going to write here 867 and let's see, we'll divide it by 255. This is going to go 3 times. It's 867. This is going to go 3 times and we'll get 765 here. So we'll get 2 here, then 0, then 1. So we are left with 102 as the remainder. So dividend is equal to divisor into quotient plus the remainder. So we have a non-zero remainder here. So we'll apply the Euclid's division algorithm with to 255 and 102 again. So we'll be repeating the steps. So 255, we are going to divide by 102. This will go 2 times and we'll get 204 here. And then we'll be left with 51 as the remainder. So we'll put it in this form. Dividend is equal to divisor into quotient plus the remainder. Now we have 51 as the remainder. Again, it's non-zero remainder. So we will proceed further with the same steps. So as we can see, 102, if we divide by 51, this will go 2 times and we will get 102. And finally, we have 0 here. 0 is the remainder here. So we have dividend is equal to divisor into quotient plus the remainder. Now the remainder as this step is 0 finally. So we'll stop here. So HCF of the given numbers, we have 867 and 255. 867 and 255 is, so we have the divisor at the last step. That's 51 in this case. So the HCF for this is 51. Have you all understood, children? Okay, now I'm discussing question number 2 of NCERT. This is also based on Euclid's division algorithm. And please be very, very attentive because this is something very new to you. So I'll be explaining this question twice. You need not worry about that, but please be very, very attentive. Show that any odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. So we have to take an odd integer. So in this case, let us take a, that's an odd positive integer, and let us take b as 6. So we have two numbers, a which we have taken it as an odd integer and b we have taken as 6. Now coming back to Euclid's division lemma, please go through this again. Given two positive integers a and b, there exist unique positive integers q and r satisfying a equal to bq plus r, where 0 less than equal to r less than b. So I'm going to apply this concept in this question. So I have two integers a and b. So here there exist unique positive integers q and r. So that's by Euclid's division lemma, such that a is equal to bq plus r, where 0 less than equal to r less than b. So here a we have taken as any odd integer. I'm going to write a as it is. B we have taken as 6. So in place of b, I'll write 6. So I have a is equal to 6q plus r, where 0 less than equal to r less than 6. In place of b, I'm writing here 6. Now 0 less than equal to r less than 6 means r can either be 0, it can be 1, 2, 3, 4 and 5. Please notice r cannot be 6, it is strictly less than 6. So here we have in all 6 cases where r is 0, r is 1, r is 2, r is 3, 4 and 5. So these 6 cases we are going to consider. So coming to case 1, when r is equal to 0. So if I put r is equal to 0 here, I'm going to get a is equal to 6q. So if r is 0, even if I not write plus 0, that's okay. It will not make any difference. Now children, please notice 6 is an even number. I'll just write here even. And q is any number. Q is any integer. So an even number multiplied by any number will give us even only. So I can say that 6q is an even number. So in this case, I can say that a is also an even number. But that's not possible, because right in the beginning, I took a as an odd integer. So if I'm saying 6q is even and a is odd and they are equal also, that's not possible. That's a contradiction. So I'm going to rule out this possibility. So r equal to 0 is not possible. Now let's come to the next step where r is 1. Let's see. If I take r is equal to 1, then if I put here 1, a is equal to 6q plus 1 if I take, I'm going to get a is equal to 6q plus 1. So as just discussed with you, 6q is even. I have 6 an even number, then I'm multiplying it with any number, it would be even only. And then I have odd number here. 1 is an odd number. So even plus odd will give us an odd number. And we also know that a is also an odd number. So this case is possible. So I can write a, that's an odd integer, as 6q plus 1. Now in the same way, I'm going to proceed further. So we have r is equal to 2. R is equal to 2. I'll put 2 here. So this will become a is equal to 6q plus 2. So 6q is even and 2 also we know it's even. Even number added to an even number will give us even only. So this is going to become even and this is odd. Not possible at all. So we'll rule out this possibility. It's a contradiction. Now coming to the next step where we take r is equal to 3. So we'll get a is equal to 6q plus 3. This is even and this is odd. Even plus odd will give us an odd number, and a also we know is an odd number. We took this as an odd number right in the beginning. So this case is also possible. So we can write a as 6q plus 3. Now proceeding further, we'll take r is equal to 4. So we have a is equal to 6q plus 4. So this is even. This is also even. We are going to take even plus even as an even number. So this case is also possible. So it's this here we have even and a is an odd integer. Not possible at all because we are getting an odd number equal to an even number. That's a contradiction. So we'll rule out this possibility also. Now coming to the last case where r is 5. So we have a is equal to 6q plus 5. This is an even number and this is an odd number. Even plus odd will give us odd, and a is also an odd number, so this case is also possible. So children, please notice a, that's an odd integer, can be written as 6q plus 1, can be written as 6q plus 3, or can be written as 6q plus 5. So we have arrived at the conclusion that any odd integer is of the form 6q plus 1 or 6q plus 2 or 6q plus 3. Now let us proceed further. Now coming to the next question, I'm reading the question from the book here. That's question number 4 given on page number 7. Just give me 1 minute. I'll just erase this. Children, can you see the PPT on my screen? Okay, now coming back to this. So the next question which we were discussing, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So we are going to take any positive integer. Let us take a as an any positive integer. So we have a as an any positive integer. So we've taken a as an integer, and let us take b as 3. So we've taken here b as 3. Now please notice here, we are going to apply the Euclid's division lemma. So I'll just read out this again for you, since this is something very new to you. Given two positive integers a and b, there exist unique positive integers q and r, satisfying a is equal to bq plus r, where 0 less than equal to r less than b. Now here a is any positive integer and then b is 3. So we are going to put this in the Euclid's division lemma, and we are going to write this as a is equal to bq plus r, where 0 less than equal to r less than b. So here we have taken b as 3. So we are going to get a is equal to 3q plus r, where 0 less than equal to r less than 3. That is 3q plus r, and we can write this as r is equal to 0, 1 and 2. So we can take any of the numbers here, 0, 1 and 2. Now what we can do here, we are going to take cases one by one. So please notice in the question it's given the square of any positive integer. We are not talking about a right now, we are talking about the square of a. So I'm going to take a is equal to 3q in the first case. That I've taken because I've taken r is equal to 0. So if r is 0, this is going to become a is equal to 3q. Now when we square both the sides, we are going to get a square is equal to 3q whole square. I just write it neatly here. A square is equal to 3q whole square. Now when we write this, we can write this as 9q square, and then we can write this as a square into 3 times of 3q square, and this can be written as a square is equal to 3m, where m is this is q square is here, it's not the whole square. We can write this 9 as 3 into 3. 3 I have taken here, and this 3q square we have taken separately. Instead of 3q square, I'm writing here m in the next step. This I'm replacing by m. So this will be 3q square. So this m can be any integer. So coming back to the question, the square of any positive integer is either of the form 3m or 3m plus 1. So in the first case, where r is 0, we have taken a as 3q, and then we have got the square of a as 3m, where m is 3q square. That's actually any integer. Now coming to the next case, where r is equal to 1. So if r is equal to 1, I'm going to put here, r is equal to 1, I'm going to put here. So I'll get here a is equal to 3q plus 1. Now as per the question, I'm talking about the square of a. So I'm going to square both the sides. So I'll get a square is equal to 3q plus 1 square. Now this is of the form a plus b whole square. Children, please notice that's a very, very common mistake. Children, write it as 3q square plus 1 square. Don't do that. Do not forget to write the 2ab term. So in grade 8, you might have studied this. You've studied this in grade 9 also. I'll just write it quickly for you. So a plus b whole square can be written as a square plus 2ab plus b square. So a lot of times children forget this 2ab term. Don't do that. This is very, very important. Otherwise, it will completely go wrong. So now this is a square is equal to 3q square plus 2ab. That's 2 into 3q into 1 plus 1 square. So this can be written as 9q square. You can combine this 2 into 3q into 1 will give you 6q, and this 1 square is 1 itself. So now after this, I'm just writing here since I don't have space. So coming back to this one, we can just combine this and we can write this as 3 times of 3q square plus 2q. Please notice we have taken 3 common from here. Okay, we have just taken 3 common. Though q is also common, we could have taken that, but we haven't taken since it's not required. Because we want to put this in the form of 3m plus 1. We're not bothered about that q. We just want 3 times of something. That something is this integer. And plus 1, I'm writing as it is. I've taken 3 common only from the first 2 terms. So this is 3m plus 1. This is 3m plus 1, where m is any integer. So coming back to the question, we have now proved that the square of a, when we were taking case 2, that's r equal to 1, is of the form 3m plus 1. So we're done with this. It's 3m plus 1. Now let's talk about the last case where r is equal to 2. So when r is equal to 2, we are going to get a as 3q plus 2. So we want to prove square of a. We'll again take square of a on both the sides. So we'll get 3q plus 2 square. And we can just open the bracket here. We can write it as a square plus 2ab plus b square. So I am referring to this particular identity. It's a square plus 2ab plus b square. Now, this can be written as a square equal to 9q square. And you can combine this. You're going to get here 2 into 3, 6 into 2, that's 12. 12q plus 4. Now, somehow we need to put this in the form of 3m plus 1. So we can write this as 9q square plus 12q, and we can write this 4 as 3 plus 1. So I'm just breaking this 4 and I'm writing it as 3 plus 1. Now from these 3 terms, I'm going to take 3 common. So we'll get 3q square plus 4q plus 1, and this plus 1 I'm writing as it is. So this is 3m plus 1, where we have m as 3q square plus 4q plus 1. So square of a we have written in the form of 3m plus 1. So finally, in all three cases, we have proved that a is any positive integer and it can be put in the form of 3m or 3m plus 1. Like in first case, it was 3m, and in the other two cases, it was 3m plus 1. I hope you've all understood this. Okay, now coming to the very basic thing, I think this you already know from primary classes, but then we have put this in the form of theorem in grade 10. It's fundamental theorem of arithmetic. Now this fundamental theorem of arithmetic says every composite number can be expressed or can be factorized as product of primes. And this factorization is unique apart from the order in which the prime factors occur. So before I begin to explain the statement, I'm going to talk about composite number and prime numbers. So this you might have studied in grade 6 also, but we'll just quickly revise the same. So prime numbers are those numbers which have only two factors, 1 and the number itself. Like for example, if I take 7, 7 has only two factors, 1 and 7 itself, and nothing else except that. Let's take 23. 23 comes in the table of 1 and comes in its own table, that's 23. So it has only two factors, 1 and the number itself, that's 23. So all the prime numbers, they have just two factors, not more than two factors they have. They're called, the numbers having just two factors, they're called prime numbers. And then comes composite numbers. Composite numbers are those numbers which are not prime numbers. That means, as I just told you, that prime numbers, they have only two factors, not more than that. So the numbers having more than two factors, they're called composite numbers. Like if I take 4, 4 comes in the table of 1, in the table of 2, and in its own table. So I can say 1, 2, and 4, they're all factors of 4. So clearly, 4 has more than two factors. Let's take 10. 10 has factor 1, 2, 5 and 10 itself. So we have 4 factors here. It's more than 2. So 10 is a composite number. Now also I want to discuss one more thing with you, that as I just told you that prime numbers, we have 7 and 23. I've just given you 2 examples. So let us just quickly list the prime numbers right from the beginning. So if I have 1, is 1 a prime number? No, it's not a prime number. It's not even a composite number. So 1 is a special number. It is neither composite, it's nor prime. It's a special number. It is neither composite nor prime. So that's very, very important, children, because a lot of times children take this 1 as a prime number. Like this was a few years back, there was a board exam where there was a question that you were supposed to find the mean of first 10 prime numbers. So a very common mistake came up. A lot of students started the prime numbers with 1. So that is why I'm discussing all this, because all this you will not be using just in this chapter. You might be using in other chapters also. So if you just, so I'm just coming back to that thing, that incident, that a lot of students, they started the prime numbers with 1. So when you just pick up the prime numbers incorrectly, then your mean will also be incorrect. Okay, so let's take the next number, that is 2. So 2 is a prime number. It's a prime number. It comes in the table of 1 and its own table. There's no other factor of 2. It has only 2 factors. It's an even prime number and it's the smallest prime number. It's the smallest prime number. It's the only even prime number. You cannot think of any other even number which is prime. Only 2 is an even number. Also, it is prime. Okay, so we have 1, then we have 2. 1, as I just told you, it's a special number. Then 3 is a prime number. 4 is a composite number we've just discussed. 5 is a prime number. 7 is a prime number. Please notice 9 is not a prime number. So that's also a very common mistake. Children take 9 also as a prime number. It's not a prime number. So then after 9 we have 10. It's a composite number. 11 is a prime number. And then you can just take the you can just list it, and so on. So coming back to fundamental theorem of arithmetic, I'm reading it again for you all. Every composite number can be factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Like for example, I've taken 18 here. I've written 18 as the product of primes as 3 into 3 into 2. And then I've written it as 2 into 3 into 3. Please notice 18, as I just told you, the prime factorization is unique. We can write 18 as product of 3, 3 and 2. We cannot write it as 2 and 5. We cannot write 18 as 2 into 5. That's not correct. We cannot write it as 5 into 7. That's not correct. So the prime factorization has to be unique, but the orders in which the prime factors occur, they can be different. We can put them in different order. We can write this 3 into 3 into 2 as 2 into 3 into 3 or 3 into 2 into 3. We can rearrange them, but then we cannot change the factors. So I'm just winding up. So I just explained you that we are going to rearrange this. There's a reason behind rearranging. We can write 2 into 3 as 3 into 2. That we can do. Both of them will give us the same result, 6. And that is by the commutative property of numbers, commutative property of positive numbers. That's natural numbers we have. Commutative means that we can change places. We can put them in different orders. Still, we are going to get the same result.